Okay. So the basic idea is that instead of taking the formalism... Sorry?
If you click on more, I think there's a way to hide the...
Yes, I hoped so. Thanks so much. Thanks so much. Okay. Okay. So what people do, what I want you to do, is not to take the formalism as a given, right, and trying to make sense of quantum mechanics by reading of an ontology from the mathematics involved. Instead, the basic idea, is that we should aim at finding clear physical principles from which the formalism can be derived or reconstructed. So, one reason for doing this, is the hope that we can gain a better understanding by showing from which principles the formalism follows, right? So, of course, this is highly technical, and the main procedure is a technical procedure, namely to show how the formalism can be derived from certain principles. So it's a basic kind of axiomatization. But the hope is that this is not just, some technical exercise, but that what results from this, what we gain from this, is a better understanding of quantum mechanics. One reason why people believe that this might work and that this might be fruitful is by considering the analogy to special relativity, right? So here the idea is that Einstein did not invent or discover the mathematics of special relativity, but what he achieved was to show how the formalism follows from two principles. So in the case of Einstein, the light principle or the light postulate and the principle of special relativity. And typically we would say we do not understand special relativity because we have a mathematical grasp of the formalism, but we do understand special relativity, if we do, because we understand the principles, all right? We understand the principles from which the formalism follows. Then, of course, this original Einstein understanding of special relativity is not the only way to, so to speak, reconstruct special relativity, right? The formalism follows from the two principles of Einstein, but it also follows from the single postulate of Minkowski spacetime. And again, this then sheds some further light on the underlying physics. And we will return to this topic, whether there should be one perfect reconstruction or whether it's possible that we have different axiomatizations that are all, so to speak, equally valid, each shedding new lights on the formalism. So I just give you 3 or 4 quotes to get a better understanding of this, because not everybody who is joining us today is explicitly working on quantum reconstructions, so it might be nice to have some quotes. So the first one is from Rovelli. He says, "Quantum mechanics will cease to look puzzling only when we will be able to derive the formalism of the theory from a set of simple physical assertions, postulates, principles about the world. Therefore, we should not try to append a reasonable interpretation to the quantum mechanics formalism, but rather to derive the formalism from a set of experimentally motivated postulates." So here he very precisely specified the goal of what I take to be the main goal of the quantum reconstruction program. In the 1999 paper, Zeiling expressed very similar ideas, pointing out that this principle from which we want to derive the formalism, from which we want to reconstruct the formalism, should be a foundational conceptual principle. So I guess this is to say, this is, like I said, it's not just a practice of axiomatization, right? It's not just a technical endeavor. What we want to do is to gain a better foundational conceptual understanding of the theory. And what we want to find is this conceptual foundation of the theory. As I said, since there might be different reconstructions, maybe it's a bit difficult to pin this down, right? What is the foundation of quantum mechanics? Maybe it's not possible to get towards the foundational core of quantum mechanics in the sense like there's a unique reconstruction or a unique foundational principle, but something like this would be the basic idea. And this is how Chris Fuchs put it. He said, "We need to reduce quantum theory to 2 or 3 statements of crisp physical significance. In this regard, no tool appears to be better calibrated for a direct result than quantum information theory." Right? So far, I've talked about the main issue of reconstruction, to find a set of principles from which the formalism can be derived. As a matter of fact, when we ask what are those physical principles, right? We want to know what are those physical principles from which we derive the formalism. And it seems that principles that are particularly relevant in this context, that are particularly fruitful in this context, turned out to be principles of quantum information. So information theoretic principles, and typically the principles from which the formalism has been reconstructed so far. So typically these reconstructions operate in an operational framework, and the principles are information theoretic principles. This is a more recent quote, and I think, so this is a bit longer, but as I said, we have a lot of time. So this is, I think, also a very good quote, capturing very nicely the main idea. It says, in short, the postulates of quantum theory impose mathematical structures without providing any simple reason for this choice. The mathematics of Hilbert spaces is adopted as a magic black box that works well at producing experimental predictions. However, in a satisfactory axiomatization of a physical theory, the mathematical structures should emerge as a consequence of postulates that have a direct physical interpretation. By this we mean postulates referring, for instance, to primitive notions like physical system, measurement, or process, rather than notions like Hilbert space, C algebras, unit vector, and self-adjoint apparatus. Okay, and this is something I think that is very nicely captured in this quote, namely that one basic idea of the reconstruction program can be formulated as such that we want to know where the mathematics comes from, right? So often physicists working on reconstructions would say that what philosophers of physics are doing when they're concerned with interpretation is more like look at the formalism, look at the mathematics, and then make ontological sense of the mathematics. What people working on reconstructions want to do is to show where the mathematics comes from. Okay, so I'm not a historian, but maybe it's nice to have some idea of the background of the whole reconstruction program. So since the very, very earliest axiomatization in 1932, some physicists have always been interested in this question, right? How to make sense of the mathematics, how to perhaps find a different operational-based reconstruction, axiomatization. In this context, it is often said that von Neumann said to Birkhoff, I do not believe in Hilbert space anymore. It is said that the joint work by von Neumann and Birkhoff on quantum logic can be seen as anticipating this reconstruction movement. And of course, Wheeler's questions, why the quantum and it from bit, are like some of the most famous slogans in this context. Why the quantum in the sense of reconstruction, right? Why is it that the world is quantum mechanical? In the context of reconstructions, the question might even be slightly different, right? The question might be, why the quantum and not something even more crazy? Because typically this operates in the framework of general probability theory. I'm trying to show how quantum mechanics follows uniquely from a certain set of plausible principles. We will come to this later in more detail during the whole conference. And it from bit, of course, in the context of quantum information theory. So this, it's just for fun. It's a very rough timeline. And like I said, so Birkhoff and Neumann are typically seen as some of the founding fathers of this. The French physicist and philosopher Paulette de Douche-Février can also be seen as working on this. She is unfortunately not very well known. And then I guess the first paper that kicked off and very precisely articulated the basic idea of the reconstruction program is Rovelle's relation quantum mechanics that I already quoted. We also saw quotes from Zeilinger and Fuchs. And then Hardy's 2001 paper can be seen as the first successful reconstruction. Okay. And like I said, Philipp will talk more about the state of the art of the reconstruction program. Now I want to briefly share some thoughts, discuss some ideas that are particularly relevant for me. So I'm happy for any kind of input or discussion that might emerge out of it. And this is precisely the relationship between the program of reconstruction and the program of interpreting quantum mechanics, right? Okay, so just to repeat the basic idea. The basic idea is that we should not take the quantum formalism as a given, but instead try to see where it comes from, right? Find the underlying principles. As I said, some physicists criticize how the procedure in philosophy typically works. So here's a quote from Fuchs and Stacy. They said the strategy of mainstream philosophy of quantum mechanics has been to reify or objectify all the mathematical symbols of the theory and then explore whatever comes off the move. And it has also been said that this reconstruction program can be seen as a more physical and less mathematical approach. But like I said, the question that I'm concerned is how can we more concretely specify this relationship? How can we specify the relationship between reconstructing quantum mechanics and interpreting quantum mechanics? And what you see on this slide here, it's a map of options, right? It's like some possible options how you could describe this relationship. And just to be sure, it won't come as a surprise to you that so it's not a huge spoiler, right? So I will argue in favor of 5. I would say that 1 and 2, 3 are completely misleading, or at least 1 and 2 are completely misleading. Okay, but let's go for it step by step. One could say that the quantum reconstruction program is simply a novel interpretation among interpretations such as the many worlds interpretation and Bowman mechanics. Wrong. One could say that the quantum reconstruction program is inconsistent with, so PQI simply is interpretation, right? Interpretation of quantum mechanics. So that the reconstruction program is inconsistent with the interpretation program in the strong sense that if one program is successful, the other one is not. If quantum reconstruction program succeeds, any existing interpretation must be considered wrong. This is wrong. 3 is the following thesis. The quantum reconstruction program is in strong tension with the program of interpretation in the following sense. If the reconstruction program is successful, then the program of interpretation is superfluous. There is no need for further interpretations. And yes, I would believe that this is also wrong, but this is, I think, something that can be considered, or that has to be considered more, that we need to discuss, because it seems that some people, at least working on reconstructions, would feel like this, right? They would say, if we succeed in our reconstruction, then there is simply no further need for interpretation. That's how many physicists working on quantum foundations, working on reconstructions, feel about this relationship. And I want to share some thoughts on why I believe that this is not entirely correct. The 4th option would be to say that the quantum reconstruction program and the program of interpretation are more or less unrelated projects. The reconstruction program is equally consistent with any existing interpretation. And I believe that this is how most philosophers feel about it, right? So I said already in the beginning that unfortunately in contemporary analytic philosophy of physics, the reconstructions are typically ignored, or at least not widely discussed. And I guess that one of the reasons for this is that philosophers feel like option 4 about this relationship between reconstruction and interpretation. In the sense, yes, reconstructions are nice, but they cannot really tell us how we should interpret quantum mechanics, how we should understand quantum mechanics. I will also argue that perhaps the underlying reason for why philosophers feel about this relationship like option 4 is that in fact the quantum reconstruction has some implications that are not very consistent with how mainstream objectivist interpretations of quantum mechanics feel about how they think we should understand quantum mechanics. Okay, so I am in favor of option 5. What is option 5? I would say that quantum reconstruction program and the program of interpreting quantum mechanics are complementary projects. In the following sense, the success of one does not rule out the success of the other. Both projects can benefit from each other. Reconstructions are themselves in need of interpretation. I will say something on this because first, I think it's true. Second, I think it sounds cool. And third, I think it's important regarding precisely this underlying idea of many people working on reconstructions, that reconstructions make interpretations like superfluous. Fourth, quantum reconstruction program has some strong implications for how we interpret and should understand quantum mechanics. and in particular that the quantum reconstruction program puts some pressure on objectivist psi-ontic interpretations of the wave function. And I will emphasize this a couple of times. I do not say that the quantum reconstruction program shows that objectivist interpretations like many-world interpretation, Bowman mechanics, etc., that they are wrong, but I would say this suggests that we should look for alternatives and that they put some pressure on these interpretations. And I will try to make clear why I feel like this, and I hope that we can then discuss this today after this talk through the whole conference, so however it works best. Okay. So it seems when you look at the slide that the claim 1 and claim 2 are okay-ish. I think they don't need a lot of discussion, but the claims 3 to 5 might be in need of clarification. So why do I say that reconstructions are themselves in need of interpretation? I specify 2 reasons. First, as I have already teased, there's no unique reconstruction, right? There exist several different reconstructions of quantum theory, and it does not seem like we should expect that there's one privileged reconstruction. Like I said, this is a similar situation to special relativity, where we can derive the mathematics from, for instance, Einstein's original 2 principles, or we could also reconstruct it, derive it from the single postulate of Minkowski spacetime. It's not, at least, of course, many philosophers feel like there's one more privileged than the other, right? Many philosophers feel like the Minkowski way is the more fundamental one, is the way to go. But it seems to me that it's quite helpful to think of it as different perspectives shedding light on the same formalism, emphasizing different aspects that are relevant in different contexts. So the attitude would be that each successful reconstruction is valuable and contributes to shedding light on particular features of the formalism. As Müller and Massan have put it, every axiomatization has its own benefits. And like I said, there are some similarities then to special relativity. So the second reason why I believe that the reconstruction program cannot simply make interpretations superfluous is that there is no unique mathematical representation of the physical world, right? So the first point was there's no unique reconstruction, and the second one is that there's no unique mathematical representation. And the point is that physical theories, even if they can be reconstructed from clear physical principles, always involve notions, terms, concepts, etc., that are in need of interpretation. And we don't have, I guess, to think about very sophisticated, celebrated cases like the ADS-CFT conjecture to make this point, like to talk about dualities in physics. I think we could also, at least to some degree, make this point by pointing out that even in classical mechanics, right, we have different frameworks like Newtonian, Lagrangian, Hamiltonian frameworks to solve the same physical problems, and it's not like one framework is privileged for the others. And if you would just consider one of them, like let's say Hamiltonian formalism, you would have a very different conception of classical mechanics than if you see it from the Newtonian perspective. Okay, and this might also be a bit interesting for people working on reconstructions, because people working on reconstructions, they're typically very much like Wheeler, right? And Wheeler also emphasizes this point that we don't have this perfect coincidence or like unique representation or like perfect fit between the mathematics and the physics. So Wheeler says that mathematical models and concepts can only approximate physical reality. He says that they only can be seen as approximate words for an underpinning pre-geometry. And in this last quote, he says, the central lesson of the quantum has been stated in the words, no elementary phenomenon is a phenomenon until it is an observed, registered phenomenon. Why this is important in our context is precisely the point that even if we have a very nice reconstruction, typically there will also and always and necessarily be terms involved that we need to interpret, and we cannot expect that to have this one perfect mathematical fit between physical theory and physical reality. Okay, so how to specify this relationship between reconstruction and interpretation? The idea that, for instance, has been pointed out by Philipp Goyal is that we first need to identify the clear physical principles from which the formalism can be reconstructed, and what we then interpret is not the formalism, but precisely those physical principles, right? So he calls this a two-step reconstruction-based strategy that consists of step one, reconstruct the quantum formalism. So first, reconstruct the quantum formalism with the specific goal of distilling the full physical content of the formalism into physical principles and assumptions that can be expressed in natural language and that are amenable to philosophical reflection. And then second, interpret the reconstruction. Second, reflect on the principles and assumptions of the reconstruction, bring to bear whatever philosophical traditions may be appropriate. Okay, so this would be the idea. You reconstruct the formalism, and then what you do is you interpret the principles. Alternatively, and perhaps this is just terminology, you could say you reconstruct the formalism, and then you interpret the formalism in light of the very principles from which you have reconstructed it. Okay. So why do I believe that the quantum reconstruction program puts some pressure on typical psi-ontic interpretations of the wave function? Okay. So the thesis is the operational framework in which the quantum reconstruction program operates, or at least typically operates, is at odds with the mindset of standard philosophy of physics. So one question is, what do I mean by the mindset of standard philosophy of physics? And I think that the following two quotes that are very precise and interesting very well capture what I think is perhaps problematic about this mindset. So here is a quote by Tim Maudlin. He says, a precisely defined physical theory would never use terms like observation, measurement, system, or apparatus in its fundamental postulates. It would instead say precisely what exists and how it behaves, right? So this is the idea that in your physical theories, you represent external objects and your equations determine the behavior of these objects, how they evolve in time, right? Like it worked in classical mechanics and so on. The second quote says the following: the dominant strand in philosophy of quantum mechanics seeks to, and now the quote begins, develop an objective description of nature in which measurements are subject to the same laws of nature as all other physical processes. And they typically insist that the goal of physics must be to formulate theories that are so clear and precise that any form of interpretation is superfluous. Okay? So here again, we find this idea that interpretations are superfluous. If we have found this correct physical theory. And again, I believe that this is a little bit naive. It seems a little bit naive to me to believe that really any form of interpretation is superfluous once you have found the theory, right? Because like I precisely said, I don't think that we should expect that there's this perfect match between the math and the physics. I don't think that we should expect that there's this unique mathematical grasp that we can have on physical reality and so on. Okay. So why is this at odds with the mindset of the quantum reconstruction program? Because as expressed in the quote by Maudlin, it is typically said that your understanding of nature or your physical foundational theories must get rid of any subjective operational terms like measurement, for instance, right? Or information. And proponents of the quantum reconstruction program, they go in the opposite direction, right? They would, there's a quote, characterize quantum theory as a theory of information. They would say that quantum physics is an elementary theory of information. They would say that, this is a quote from Jeffrey Boop, that quantum theory is a theory about the representation and manipulation of information, which then becomes the appropriate aim of physics, rather than a theory about the ways in which non-classical waves or particles move. And this is a quote from Höhn and Wever. They say, the successful reconstruction from this perspective underscores the sufficiency of taking a purely operational perspective, addressing only what an observer can say about the observed systems in order to understand and derive the formalism of quantum theory. ontic statements about reality underlying the observer's interactions with the physical systems are unnecessary. When I have had an email conversation with Philipp Berghofer, he told me that a couple of years ago he felt differently, right, about this relationship between reconstruction and interpretation than he feels now. I don't know exactly how he feels now. I'm very happy to find this out today. I just want to say, I like this statement, right? I like this to say that the way how reconstructions, if they're formulated in an operational framework based on information theoretic principles, how they put pressure on typical psiontic interpretations is that if it turns out that it is sufficient for our understanding of quantum mechanics to think of the wave function in some informational language, then this brings up the question, right, why should we make the stronger ontic claim that the wave function represents or something real, right? First of all, there's wave function realism, right? The idea that the wave function actually is a physical object. Why should we believe this if it leads to several conceptual problems? Secondly, there's the idea that the wave function represents physical reality, some underlying physical reality. But that this also leads to several philosophical problems, right? It seems like there are basically two ways to have an observer-free interpretation. It would mean either to accept many worlds or to modify the formalism. But why should we modify the formalism of our most successful scientific theory, right? Why should we do so if we can make sense of it in terms of information?
Do you take questions?
Sorry?
Do you take questions?
Yes, I do take questions at the end. Okay, so the thesis is, the more evidence we have that quantum mechanics is fundamentally about information, the less reason we have to believe in an objectivist interpretation that seeks to purge quantum mechanics of all operational notions. And this is why I like to say that the success of quantum reconstruction program might put pressure on objectivist interpretations. And I believe that this would also be basic direction in which, for instance, the cubists are going. Again, we have a number of cubists present, so I'm happy to find out if they feel like this. So here's a quote from De Broter, who's also here, so we will find out how he feels about this. And Stacy, and they say, a quantum state encodes a user's beliefs about the experience they will have as a result of taking action on an external part of the world. Among several reasons that such a position is defensible is the fact that any quantum state, pure mixed, is equivalent to a probability distribution over the outcomes of an informationally complete measurement. Accordingly, cubists say that a quantum state is conceptually no more than a probability distribution. So what is interesting for me is this accordingly, right? The idea that once we can successfully make sense of the wave function in this way, why should we make any stronger ontological claims from the very beginning, from the very get-go? It seems not plausible to do this. Okay. So this would be how I think that the quantum reconstruction program can put some pressure on psi-ontic interpretations. There's also a more indirect way to proceed that has been articulated by Markus Müller and Adam Koperinski. They say none of Bowman mechanics, erratum quantum theory, or collapse theories fill the explanatory role of a principal theory. For example, erratum quantum theory does not start with a broad general framework of theories of many worlds, put simple principles on top of that, and prove that quantum theory is the unique theory of many worlds that satisfies these principles. And again, I think I agree with this general idea. So here the general idea is that quantum reconstructions, if we have a successful reconstruction, our successful reconstruction can be viewed as a principal theory in Einstein's sense, right? So Einstein believed that special relativity, for instance, is a kind of principal theory. And the idea would be that other interpretations of quantum mechanics, like, not other, but objectivist interpretations, psi-ontic interpretations of quantum mechanics, like erratum quantum theory, they cannot do the same as reconstructions can do. Of course, proponents of, for instance, the many worlds interpretation, they would say, yes, this is no surprise because what you have done is to provide us with a principal theory, but what we do is provide this more of classical view in the sense that our theory represents physical objects and determines how they behave in time. Yeah, so I think that Müller and Koperinsky make a very important point, but I hope, or I believe that we could make a more direct, or find it more direct argument of how reconstructions can put pressure on objectivist interpretations. And thank you so much for your attention. And as I said, now Philipp will continue with the more.
Actually, if you want to take questions.
Okay, so yeah, thanks. Okay, so let's do questions now. Then Philipp will provide us with an overview and yeah.
Could you pass this along?
Oh, thank you. I'm curious to understand why reconstruction, the reconstruction program, is sort of synonymous with an informational theoretic approach, or with because I mean, of course, I'm very sympathetic to interpreting wave functions subjectively, and I'm not that interested in objectivist approaches. But if I hear the idea of a quantum reconstruction program and everything you said, sort of leading up to this thesis, I can see no reason why an objectivist wouldn't also engage in reconstruction, just taking different physical principles to start from. So I would be very much interested to hear how you defend that identification.
Yeah. So if I understand you correctly, you would say, of course, also people believing in objectivist interpretations like Bowman mechanics, Manuel's interpretation, can have, of course, interest in reconstructions, right? And that there's no prima facie tension between those two projects, right? This is the gist of your comment. And okay. So I would say yes, of course. We should, in principle, be interested in reconstructions, right? Maybe to make some details more precise and whatever. But what I tried to argue is that the overall underlying idea of the reconstruction program is already in some kind of a tension with the objectivist interpretations, because typically how objectivist interpretations proceed is by taking the formalism as a given and trying to make sense of it directly. Like you start with interpreting the wave function, and the reconstruction, or like at least some proponents of the reconstruction program would say that before we try to make sense of the mathematical terms involved ontologically, we should find out where the mathematics comes from. So I think already at this level there's some kind of tension. And then, as I tried to argue, since the successful reconstructions operate within an operational framework that does not get rid of the notion of measurement, for instance, and because of the fact that they make sense or try to make sense of the formalism in terms of information theoretic principles, it seems that there's this further tension, because if the notion of information, for instance, is in some way fundamental for quantum theory, then it's not so obviously clear why we should get rid of operational terms before we interpret quantum mechanics, right? Because in this quote, for instance, of Maudlin, he says a precise physical theory needs to get rid of all operational subjective terms. But why should this be true for quantum mechanics if quantum mechanics is foundationally about something like information? So this is why I think that there is this kind of pressure. And like I said in this quote, right, the more evidence we have that quantum mechanics is fundamentally about information, the better we can make sense of quantum mechanics within an operational framework, the less reason we have to make additional ontological claims that state that the wave function is something that exists physically, represents something that is physical, and so on. Like this was the main idea.
Thanks. Could go back maybe to slide 19, I think. That's what I said. Is that it? Yeah, I'm not, it's like, I'm not convinced I understand this so much. Maybe if you could unpack this a little bit more. The reason I'm a little bit hesitant here is because I guess it depends on what the reconstruction. I guess it relates a little bit to Rudiger's question. I mean, it depends on what the reconstruction is about. If it's an operational reconstruction, then like it's very closely tied to experiments. There's a sense in which the interpretation needed in that case is at least minimal. Maybe not needed at all. I mean, it's clear that you know what you're doing when you're interacting with your experimental devices, for instance. At least someone might claim that. So I'm not saying that I think that's right necessarily, but I'm just wondering if you could maybe just unpack that a little bit more.
Yeah, absolutely.
Because I mean, the main point I want to make is that it's not clear necessarily. It might depend on the reconstruction whether that's true or not. In some cases, one might argue that it's not true.
Yeah, I think you're absolutely right that how exactly then this works out, how exactly we have to consider this relationship between the theory and reality, how we interpret this relationship, very much depends then on the precise reconstruction, right? So if we have a very successful reconstruction that is very clear, makes use of clear operational language, very closely linked to experiments, as you pointed out, then there might be a very low level of need of interpretation, but still, since the quantum reconstruction program, as far as I understand the prospects of it, it will or should tell us where the mathematics comes from, right? In terms of foundational principles, but it will not get rid of the mathematics, obviously, right? So our theory will still be couched in the same mathematical language, and therefore we still need to make sense of the mathematical terms that are involved. The idea is this works the better, the clearer our reconstruction is, right? The clearer the principles are from which we can derive the mathematics, but I think that still such question of interpretation will still be relevant, and it just seems to me that basically no physical theory really is completely free or will ever be completely free of interpretational questions, like even in classical mechanics, right? I just teased at this, but we also have philosophical discussions in classical mechanics. We have also philosophical discussions in special relativity, right? Where I pointed out that there exists different formulations, axiomatizations, and so on, and also in general relativity and so on. So I just think that as long as we have scientific theories that I guess necessarily are formulated in mathematical language, we will also have some kind of interpretation involved. But you're absolutely right? So the level of interpretation very much depends on the success of the reconstruction, and the clearer the reconstruction, the clearer the underlying principles, the less need will there be for more stronger interpretations. So.
Thanks.
So I'm not sure if this is more of a comment than a question, but I was struck by your idea that the Minkowski space was a reconstruction, because the way I've been thinking about it was more like Minkowski space would be similar to, perhaps the Schrödinger or von Neumann formalism of quantum theory. It's sort of one of the more final clear forms that the mathematics took, or in this case perhaps more unique than in the case of quantum theory. And so that the Einstein principles are sort of a way of perhaps deriving that. So I'm wondering, is that confused, or it was an interesting idea?
No, so what you said is absolutely not confused. Actually, what you said might be right? And I might be misled or a little bit wrong or completely wrong about this. But the way I feel about this is as follows, right? So the view that you expressed, I think many philosophers, many physicists agree that after Einstein successfully showed how the formalism can be derived, so to speak, right from the two postulates, from ancient two postulates. Minkowski showed that we can also start by simply taking Minkowski spacetime as fundamental. And now we have learned something new, I agree. And we have learned that this Minkowski framework is more fundamental, more foundational. And this is where I feel a bit uneasy about it, where I think, okay, it's just true that we have different possible, I don't know, axiomatizations, reconstructions, different possibilities to derive the mathematics, right? One would be Einstein's original postulates, another would be taking Minkowski spacetime as the single unique postulate. But the view that I prefer is to say both ways of reconstruction, so to speak, shed new or different lights on different aspects of the same theory. Like, right, for Einstein it was, at least how, to my knowledge, he did this historically, was that then the principle of special relativity was generalized to the general principle of relativity, which was important for finding general relativity, right? So for Einstein, I guess, it would be like one virtue of his original reconstruction is that it leads us more straightforward to general relativity. The light postulate, for instance, has the very nice feature of saying something physical about the world we live in. Of course, also Minkowski spacetime tells us something important, but in a different way. So my view would be that different reconstructions, axiomatizations, derivations in special relativity are to be considered as on the same fundamental level. And I guess that this is also true so far with respect to the reconstructions that we have in quantum mechanics, namely that so far at least we have not found a unique way of, or the best way, a privileged way of reconstructing quantum theory, but people have found different ways to do so, and each reconstruction is somehow useful in its own light, but not more fundamental than the other. There is some discussion on this, right? Adlam, for instance, has argued that we should believe that some reconstructions of quantum theory are better than others, right? That they just capture better the structure of reality. So she has a more realist approach to the whole program of reconstruction. But I guess that the approach that I prefer would be, at least at first, we consider all of them to be equally important, and maybe yes, we find something like a unique privileged reconstruction, but so far it would just be more modest. Thanks.
Philip, so the basic problem with quantum mechanics seems to be that although the formalism works very well, it's incapable of being reified. So there's a distinction in the various quotes that you displayed there. There seem to me to be two kinds of quotes: those that favoured an ontology, finding an ontology that would explain the formalism, and objectifying quantum mechanics, and those that say it's unnecessary. It seems to me that you ought to have a preference for the ontology, finding an ontology that does make sense, rather than what I would say is a cop-out, trying to find an excuse for not looking for that ontology. I mean, even if we find a better information theory or any other theory that seems to work better than the present theory, the ultimate aim should be an ontic theory, an ontology that explains the formalism. That's all. Well, I should make this a question. You did state there that you don't think that it's necessary to objectify quantum mechanics, and that is your view, definitely.
Okay, thank you so much.
Not sort of a question.
Like I said, it's a very relaxed time frame that we're working in, so we can also discuss this then at the coffee break or whatever. So yes, I think I agree with some substantial statements of yours. So yes, it would be nice to have a very clear ontology, right? To have a very clear ontological picture of the field that we are working with. And obviously, this is one of the main motivations, right, for doing something like Bowman mechanics, for interpreting quantum mechanics, for instance, according to the many worlds interpretation. The idea to find this very clear ontological picture. And coming from classical mechanics, this seems very natural, right? But I think the point is, at least to some degree, that it turned out that quantum mechanics is very different from, for instance, classical mechanics, right? So interpreting quantum mechanics ontologically from the get-go, at least, having something like a psi-ontic interpretation of the wave function, it apparently leads to certain problems in particular, and I think I only tease at this very briefly, right? So the way I understand the situation is if you want to get rid in your formalism, in your quantum formalism, of any operational terms like measurement and so on, if you want to make sense of quantum mechanics without any operational terms and so on, basically, I guess you have two options, right? You accept the many worlds interpretation. So you accept that there are infinitely many unobservable worlds and that reality branches every time a quantum event takes place in all possible outcomes and so on. Or you modify the formalism. You modify the formalism like, for instance, Bowman mechanics does. Both options have some problems. Interestingly, in philosophy of physics, both options are the most prominent options, right? So most philosophers working on quantum mechanics either are in the camp of the many worlds interpretation or go in the modificatory direction, most of them in the Bowman direction. And I think what I tried to do here is to say that we should at least contemplate the idea that this is not necessary, that we can make sense of quantum mechanics without interpreting this in this stronger way, ontologically speaking. And I mean, this is just a side note, right? But it seems to me that it's a bit strange that now the current situation is that philosophers are working on modificatory interpretations, right? Which basically means working on modifying quantum mechanics. And physicists trying to make philosophical sense of textbook quantum mechanics. It seems to me that maybe it should be the other way around, right? At least more philosophers, in my view, should engage with the idea to make sense of quantum mechanics philosophically in a way that does not modify the formalism. This would be just like the basic idea. Okay.
Thank you. So, thanks, Phil. There is a sense in which the traditional debate between instrumentalism and realism in philosophy of science applies to your topic, especially the point about the reconstruction program and the interpretation program being complementary. So, what's wrong with thinking that interpretations are, as they are indeed, motivated by, uncovering the structure of physical reality while taking reconstructions more instrumentalistically, right, as being interested not in that, but in, as you put it, understanding or explaining quantum mechanics, right? So that is, taking reconstructions as tools that make us, put us in a better position to understand quantum mechanics rather than the structure of physical reality.
So I think I have so two thoughts came to my mind. First is I think this is it's very useful to consider very important discussions in philosophy of science in the context of, for instance, reconstructions. And again, and I don't want to ramble and don't want to make this point too often, but this is also strange to me that in philosophy of science, many people, so in philosophy of science, it is okay, right, if you're a philosopher who does not believe in a strong form of objectivist realism. So many people are like, for instance, say perspectivists or whatever, or like more on the anti-realist side. And again, in philosophy of quantum mechanics, interestingly, strong realist versions are much more common. But I think your question was more like, why should, for instance, I read too much into reconstructions, right? Why shouldn't we not just think of reconstructions as tools they are helpful to clarify certain points, but we should not overestimate their significance when it comes to understanding something like the underlying theory, right? Understanding quantum theory in this case. And yeah, I see that this is a very natural way to think about this. But yeah, like I already said in my first, in my reply to the first question, was that if it turns out, let's say it turns out that we can make perfectly sense of quantum theory just by thinking this informational theoretical way, what would be the motivation for making strong ontological claims if these strong ontological claims lead to something like infinitely many worlds, the necessary to modify the formalism, non-locality, and so on. But yeah. Mm-hmm.
Okay, this is going to have to be the last question.
Yeah, thanks very much for the nice overview of this whole program. So I just wanted to make a comment on this comparison to special relativity and the axiomatization. Mm-hmm. It's on the one hand, I think, very important, but I think it's also there are a couple of misconceptions involved. In fact, that's what I will talk about in my own talk later on today, by comparing the reconstruction program also to the axiomatization of special relativity. And in particular, special relativity, as we know, the mathematical formalism doesn't just follow from the relativity principle. Mm-hmm. You need a lot of additional input, in fact, and that's often just swept under the rug. And then when comparing reconstructions to special relativity in the simple principle, then often they're put in a somewhat disfavorable light because they need a lot more input in some sense. But it's not quite true, because special relativity needs a lot of input as well if you want to get exactly the mathematical structure of special relativity in Minkowski space in 3+1 dimensions and so on. So that's just I think an important point to make when comparing it to the axiomatization of special relativity to the construction program that I think is often overlooked.
Yeah. Okay, perfect. Yeah, I'm looking forward to your talk, right? I'm looking forward to this, and then we can discuss this further. Okay. So thank you so much.